Okay. So let me just say that we are pleased to welcome Lev Vaidman from Tel Aviv University.
Hello.
And that you're going to
Hello.
speak of the Lev is going to speak of the many-word interpretation as the best explanation of the results of experiments. So Lev, thank you very much, and it's up to you now.
Thank you for introduction, and I'm really sorry that I'm not in person in Paris, but I will try to do my best even in remote. So I strongly believe that many words is by far the best interpretation in quantum mechanics. And in the purpose of my talk here, and by wanting to come to Paris, and now the giving it without coming to Paris, is try to persuade more and more people that this is so. In fact, this is not a new kind of opinion of mine. I put it in writing in my first paper, which took like almost 10 years to publish. And this is its first version. So even then, this was 89. I wrote, I consider many-word interpretation being the best available quantum theory. So let me make some big words. The purpose of science. Today, Google tell us what is science. And science aims to produce natural explanation of how the natural world works. So what I think is important is to explain my experience. My experience, your experience, I don't think that everyone has very different experiments. Clearly, they are different, but this is I think, what science is supposed to do. Now, and I want to believe that my experience supervenes on some real physical world. There is some ontology. It's not only in my mind. Now, my experience are my memories, my records. And I want that my theory, which make a connection between the records of preparation with records of outcomes. There are questions, how the world started, and there are many questions. I want to limit myself to, I look on all my memories, and I look on cases which I consider as preparation of experiments. Maybe it's a real experiment in laboratory. And then I get some outcome, and I want that theory will explain this. I realize that there are two kinds of experiments. In some experiments, every time I prepare something, I get the same outcome. There are other experiments, it looks for me that I prepare the same thing, and maybe I do prepare the same thing, but I get different outcomes. In both cases, I want an explanation. First, in deterministic experiment, why I get this definite outcome. In probabilistic experiments, I think it's a good idea to explain everything. If there is something random, I don't like it. But there are facts. In my memory, there are many experiments which I remember the same preparation and different outcomes. Still, there are some regularities. Regularities is the frequency of these outcomes. So this is what I would like to explain. I believe that many-word interpretation is the only deterministic theory without action at a distance, which makes this connection, which make connection between all my memories of preparation and all my memories of outcomes. So I will start discussing classical physics and trying to say that it's great. Great for me, local and deterministic. This is what I think it's a desirable property of a theory. Unfortunately, it is wrong. Quantum physics explanation of world without quantum measurement is good. So the next step will be to try to explain all these things which were good in classical physics using quantum mechanics. And I will say that if I limit myself on cases where we do not perform quantum measurements, then quantum physics do what classical physics failed, to explain everything we see around. But sometimes we do quantum measurement. In fact, I will do quantum measurement during the talk. In this quantum measurement, I will split the word, and I will split the word in two options. In word A, I will be told to talk about paradox of interaction-free measurement. In word B, I will talk about paradox of teleportation. Why I will do this? Because many words resolve, from my point of view, all paradoxes. I don't have time here to explain everything, so I will, in fact, will explain only one of them. I will explain two. In one word, I will explain one paradox, and in a parallel word, I will explain another one. And I will finish with some summary. Okay. Classical physics. Classical physics, Newtonian physics, we can also add fields, but we have particles, they have well-defined trajectories, and we have a law how this trajectory changes with time. It's in 3 dimensions, it's deterministic. And sometimes there are experiments which look random for us, but this randomness is really kind of a practical randomness. It's because our ignorance about exact preparation. For example, if we send a tennis ball to some surface, it bounces and we know the physics how it happens. If the same surface has holes and will send a small ball, sometimes it can go through because there are holes. Sometimes it can bounce. And all this we understand because we can understand that really it's a bounce or go through because initial condition, if it go to the surface, it bounces. If it go to the hole, it goes through. And more than a century ago, physicists thought that classical physics essentially explained everything up to some details. Maxwell wrote the only occupation left to men of science to carry these measurements to another place of decimals. And the same essentially message came from Michelson. Fundamental laws and facts of physical science have all been discovered. Our future discoveries must be looked for in the 6th place of decimals. Now, they were pretty wrong, and I think this is why today people are not ready to make similar statement, although I think today they should. Classical physics provides good explanation of macroscopic objects and their behavior. We can look on tiger, we can look on a small whisker of tiger, we can look at smaller and smaller, maybe biological parts of this, or maybe even atoms. And it looks like classical physics explain it. And it explains it in a similar manner because macroscopic object or microscopic object behave in a similar way. But it fails. And this was found in the beginning of the last century. We have black body radiation, we have stability of matter. And maybe what's I like to consider, I like interferometers. At that time, this Mach Zehnder interferometer was done with light, at light waves, and there were no problem. But later, Aspect and Granger made this experiment with single photons. And they was able to tune it in such a way that it always come to one place. They repeat it, and it always come here. And according to the classical description, we cannot really fix exact shooting of our photon or whatever. So how we know that it's always do this way, that it's goes through here or bounce twice? And there is no classical explanation for this type of behavior. We need quantum explanation. And quantum explanation says, quantum physics says there are no particles. So there are particles, but all particles are waves. If particles are waves, then interferometer is something non-normal phenomena. So we send something, we send these waves, and if we arrange destructive interference, and this is exactly should be done, it's not always, we have to tune it well, our interferometer, so one port will be dark. But after we tune it, then we never get clicks here, we always get clicks here because waves go here and particles are waves. This type of experiment, quantum physics explains well. A simpler experiment, or maybe this experiment when we don't tune it properly, the quantum physics doesn't explain so well. But it's still, this kind of experiment also explained well, and they explain up to this many decimal numbers, not 6, maybe now 10. So quantum physics today, if we look on experiments which are not random, explain everything up to precision which we can measure. And maybe one can say that quantum physics is not good because there is uncertainty principle, and anyway we should, this should disturb our way of viewing the world, because even something is certain now because of delta x, delta p, and later it will not be uncertain. But this is really not true. If we'll take mass of macroscopic object into account, then delta x, delta p is not really a problem. This because of the small number of h, we can have a human, this is a small human, but I took 50 kilograms. And then I can put his position uncertainty during all his life less than 10 to the minus 12 meter. So we shouldn't worry too much. So the quantum physics, if we think about experiments which are with definite outcomes, explain everything in a very good manner. We look on this, the same picture, everything really, we don't have exact position of atoms. They are kind of well-localized packets. What we see, when we maybe will look on atoms, it's difficult, but when we look on all these macroscopic objects, it's all explained well. Everything we see explained by quantum mechanics. So we can say that psi universe is just one word, and in which this word, all objects are well localized. So they're in the product state, they are not entangled. One of them is a tiger. And this tiger has also many macroscopic parts. And these macroscopic parts are also not entangled. They're a well localized state. When we go further and further, we look on a whisker, or then we go to parts which cannot be well localized. Atom cannot be, atom must be entangled. Otherwise, it's not stable. The stability of matter, we need entanglement. But these are only for very tiny particles. We don't feel them. We feel the tiger itself, or maybe its teeth, but not its atoms. So the atoms inside the tiger and electrons and protons in the atoms will be entangled. But otherwise, everything else is not. It's just a product state. And the product state, it's like a classical story. Just instead of an exact point in any way, we cannot see exact position. So there is no difference between quantum picture and classical picture.
Lev, you asked to be interrupted. Shall
Yes.
we do that or not?
Yeah, sure.
Oh, okay, so here's a question. How do you know that something is a part of something? Is it a fact of nature? Is it your perspective? How do you know that teeth are part of a tiger, but atoms are somehow not part of a tiger, or maybe they are? So how do you establish that a system is a subsystem of another system?
Okay, I see a world around. I have to explain my experience. All what I see, macroscopic objects. So I see a tiger, and as a tiger, I hopefully it's in a zoo and its teeth don't touch me, but maybe I see them. So I have this macroscopic big description. And if I don't perform quantum experiment, I can imagine that this is all what it is. So like in the classical description, I have this tiger and other animals in a zoo, and in quantum description, I have this product state of all these macroscopic objects. I postulate that in my world, all macroscopic objects are well localized. This is like in classical world. So please tell me exactly what do you want, what was not clear, but what should I clarify?
So if you see a macroscopic tiger, you somehow know that teeth are part of that tiger because they're localized in the same place. That's what you are saying, I guess, about localization. But not, so is it true that subsystems for you are identified as a subsystem by localization? So if the spatial position is the same, then it's a subsystem of something. Is that the characteristic feature? I'm not sure how I identify a subsystem. So for example, if you just rely on your intuition and you look at the sky, then you may say, well, maybe, I don't know, maybe the air is part of the system sky. But, you know, it doesn't make sense scientifically. So just relying on intuition is probably not the best thing. So I need to have some criterion. Is it my perspective, or should it be just based on spatial location, or should it be somehow objectively true? That's what I'm asking.
So essentially, this is my last equation. Provide a connection between my ontology and experience. Currently, my ontology, it's a wave function of a universe in a product state where we don't have entanglement of macroscopic objects. So I look on this big wave function and I can calculate mathematically the density of all kind of, in this case, for example, I look three-dimensional picture of operator, the number of hair molecules in a particular volume. If I look on this, I will have a three-dimensional picture of a tiger's whisker. And this is how I make connection between the tiger's whisker and my wave function. If I look on the other parts, I will see the whole tiger.
Yeah, one last question and then I'll stop. I'm not asking about quantum states, I'm asking about subsystems. Maybe the whisker is not the tiger's whisker. Maybe it's some Martian from Mars to whom this whisker belongs. How do you know that the subsystem whisker is the tiger's subsystem and not something completely controlled from Mars? So I'm asking about identification of subsystems as being subsystems of some bigger systems, not about states.
I want to explain my experience. I came to a zoo and I see a tiger. So I write down an ontology, which I believe describes the situation. And this ontology will be a wave function of a tiger. It will be, I don't say it's impossible that maybe there are some Martian or whatever, but I don't need this assumption. This will not explain my experience. So I want the simplest theory which explains my experience. I see macroscopic objects around. I say that they're really kind of a wave function in the shape of these objects. Because for me, all objects are just wave function. There is no, there are degrees of freedom, electrons, protons, whatever, but the wave function of these degrees of freedom in the shape of a tiger is a tiger. In the shape of a table is a table. Okay, let's continue and then maybe. Okay, so this is in a special universe which has only one word, only one story, an all macroscopic object in kind of in one places. But I'm pretty sure most of you saw this cartoon. And I think this cartoon is kind of inappropriate. It says that we should worry about classical apparatus. Classical apparatus will do nothing to my world. If I have this quantum world with a single story, and I use classical apparatus, it still will be one word. What I should worry is about quantum apparatus. This is what should be forbidden. If I have photomultipliers, Geiger counters, Stern-Gerlach devices, photodiodes, this is a dangerous thing. This thing will spoil my story. So if I have a source, a beam splitter, and two detectors, if there are single photon detectors, here I have a problem. Well, what's the problem? Because my theory tells me this, my equations give me this. But yeah, I also can maybe specify my detector is photomultiplier. So, and when I apply, I see a click here, or I see a click here. But I don't have equations for this. The only equations I have when I have the wave functions and both activated, and the wave function will have both this activated and this activated. And so there is a contradiction between my theory and my experience. Again, the way out is to say there are two experiences. If I perform this experiment, then really there is there will be two worlds. In one I experience one outcome, in another I experience another one. So let me do this kind of experiment now. In fact, everyone can go to my homepage and there is a link to a word splitter, which is a quantum device. And you can divide it for 2, 3, 5, whatever. I will divide it for two words. And again, why I want to do, I have a particular purpose, not just making a quantum experiment, I will use it. And pretty long time ago, I wrote a paper which kind of showed why I believe in many worlds. I believe in many worlds because it explained some paradoxical aspects of quantum experiments. And in this paper, I was talking about two experiments. One was interaction-free measurement, and another one was teleportation. I was involved in both. So now we will make this quantum experiment, and this is my word splitter, and now I will go there. I hope you see the screen, because, and now I want to split it in two, so I will go here, and here I will write teleportation. And here I will put IFM. And when I push the split, then there will be some link and there will be some experiment. And the result of experiment we will see on the screen. So let's do this. So you're in the word teleportation. I really believe, whatever, that there is a parallel world in which we all see you're in the word IFM. But we're in the word teleportation, so I will skip. The first one was this interaction-free measurement. I will skip this, and I will go to teleportation. Okay, teleportation. It's science fiction because the matter cannot jump from one place to another. This is impossible. However, quantum mechanics essentially made it possible. How it made it possible? Because objects are not matter. Objects are shapes of the matter. If I want to move myself from one place to another, I don't have to move my electrons and protons. I am just a wave function. So all what I have to do, if I'm here on Earth and here I have to arrange particles on Moon, and then I use teleportation. And in this teleportation, it's happened that I disappear here and I appear there. My shape. The electrons from here get the shape of me there. I think most of you, probably all of you know this work, which I think made a revolution in quantum information. And it's kind of very simple protocol. If we want to talk about teleportation of spin half particle, then Alice and Bob share an EPR pair, this quantum state. Then Alice gets another particle. She doesn't know the state of the particle. She performs a measurement which is called Bell measurement, which can have 4 possible outcomes. She sent by classical channel the outcome, just 2 bits. There are 4 possible outcomes, it's 2 bits to Bob. Bob makes manipulation of his pair and he gets the quantum state. In fact, this is very simple. The original quantum state of these 3 qubits. This is qubit which Alice gets, and this is EPR, 2 EPR qubits. This is quantum state of these qubits. It can be rewritten, the same state, in a basis of Bell states of Alice's part. Alice has her particle from EPR and this other particle. We can rewrite this in Bell basis. If we write it in Bell basis, then the third particle will be essentially will know the state which Alice got. If it's a singlet, it's the state itself. If it's for all 3 others, it's rotated around different axes. So what really Alice does in teleportation, she tells Bob through which axis he has to rotate his qubit. And after the rotation, in all words, never mind what happened, Bob gets this Alice's qubit. I was very upset when I saw this paper because after I read the abstract, I knew how to do this, but I didn't ask a question. Still, I was able to add something, so I added teleportation of quantum states, essentially the same method, but using instead of singlet of EPR bomb, then singlet of EPR. And this gives me teleportation of continuous variables. So I'm kind of made of continuous variables. To teleport me, I need to take all my molecules and to perform this Bell measurement for all of them. the Bell measurement now with EPR states. And so it gives me many numbers I have to send here. And again, this is science fiction. In principle, it's simple. It's enough to teleport every of my atoms to teleport me. But there will never be technology for doing this. I don't need to teleport. It's even I teleport separately every of my atom, I will be teleported. But this is impossible, not now and ever. So, but I was talking about paradox. The paradox happening even in the teleportation of just a single qubit. The single qubit, it's a direction in space. We need two angles, two numbers. It's a lot of information. In the end of the process, the qubit is here. So this information, somehow alpha and beta are here. And it wasn't before. Alice didn't get the particle before. So clearly Bob didn't have it before. So Alice gets these two numbers, sends 2 bits, and now these 2 numbers in Bob's hand. So this is paradox. How we can send 2 real numbers, 2 angles, by sending 2 bits. In fact, there is also other kind of a paradox. When we perform a measurement on EPR pair, the Bell measurement, then we send essentially this particle. This is what the essential part. After this measurement, we had a mixture of qubits in all these directions. Now, before we had this EPR pair. After we had this mixture. So it looks like we had something, if there is only one word, so there is only one of them. So after the Bell measurement, there is a change on both sides. And this, for me, action at distance, which is paradox. Now, in many words, there are all of them together. There are a mixture of them. And quantum mechanics tells me that this mixture of all these 4 qubits is equivalent to the original mixture when it was an EPR state. So there is no this action at a distance paradox in Bell measurement. But also, this paradox is resolved. How it resolved? Maybe it's not a paradox, it's still strange. Somehow, this number is here from the beginning. Words are non-local. So this Bell measurement kind of, it's separate by local measurement for non-local words. And the only information which is sent is which word it is. There are 4 words. These are 4 different words, and the 2 bits is just information about in which word we are. This is why it's just 2 bits. The non-local story happened by this non-local wave. So we do not send the number. The only information we set is just this, the identity of a word. Okay. So let's then go to a summary. It's first the textbook quantum mechanics. In fact, I didn't talk about it before. I talk about special case where there was no quantum measurement. No quantum measurement is not this picture. In this picture, this is a real situation when we perform a measurement, and now if we believe in collapse. If we believe in collapse, we have this Schrödinger equation and collapsed measurement. Every splitting is measurement. We have to add the Born rule. If we don't add the Born rule to this probability of outcome, we can send signals faster than light. So to keep peaceful coexistence with relativity, we need Born rule. And connection, what I want, the connection of ontology with my experience. It's the same connection, what I say, which I discussed before when we had just one word. But this is, again, this is just one collapsed world. All collapsed world will have this form when all macroscopic objects are well localized. Because all measurements, if I have situation when some macroscopic object became delocalized in two places, like Schrödinger cat, it invariably collapsed to one of them. The cat is a good enough observer. We don't have in a collapse quantum mechanics, we cannot have a cat in a superposition. It will collapse to one of its state. So we have this macroscopic description of macroscopic object with internal things which are entangled, but we don't feel them. We experience macroscopic objects, and these macroscopic objects are well localized in 3 dimensions. We also have some entanglement of atoms. This is necessary to explain stability, but we don't feel it, so there is no problem with this. No macroscopic objects are entangled. In the moment macroscopic object became in 2 different macroscopic states, it collapses to one of them, according to the textbook quantum mechanics. According to the many words, it's not so different. It's the same story, we just say there are no collapses. There is only Schrödinger evolution. The connection to ontology, we have to connect to ontology. We use the same connection as textbook quantum mechanics. If we look on some collapsed world, this is what corresponds to our experience. Since there are many possible, not possible in many words, they are really all actual. In collapse, they are possible. In collapse worlds, there are many possible. Now they are all actual, but they all correspond to things which correspond to a kind of sensible experience. If I don't want to be a parasite of the textbook, then I will introduce my postulate. I say all macroscopic objects are localized wave packets. So I make this decomposition according to this. I'll have to look on all macroscopic objects and require that they all well localized. I need there are experiments in which I see results which are not deterministic. First, I say there is no probability because everything deterministic. It's deterministically all outcomes happen. For us, living in particular world, there is a feeling of randomness. It's illusion. Sometimes we can have a situation similar to a classical case where we do not know exactly the situation. But it's not the ontology. We know the ontology. The ontology is this big wave function. What sometimes might happen, we don't know in which branch we are. And then we have to use this postulate like Born rule. We have to postulate what is the probability to be in a particular world. And again, if I want to avoid superluminal signaling within the world, then I have to make this postulate that probability to find myself in a particular world, it's according to this, what I call measure of existence of a world, and which is given by the Born rule amplitudes. Okay, so according to the textbook quantum mechanics, there is this world, because it's happened in our world, just teleportation. We also can think that there is a parallel, possible parallel world, but it didn't really happen. There is only this world, according to the standard quantum mechanics. According to the many worlds, all are there. The world in which I explained teleportation and the world in which I explained interaction-free measurement. And the experience of the observer in the world is completely specified. In every world, I have experience. And it's specified by the same, the branch wave function, which is the same like the collapsed wave function. And words do not interfere. This it's important. I have to look on my Schrödinger equation and to see that in all realistic situations, I shouldn't worry. There is a parallel word in which I explain interaction-free measurement, but there will be no interference with this word. Unless there is super technology which will play games with me, but this is not feasible to assume such an assumption. So we do not experience superposition because we are capable of having only one experience of macroscopic objects of time. Other states of macroscopic objects are experienced by our duplicates in parallel worlds. There are parallel worlds. If we look on wave function of the universe, it's kind of a big mess. But it can be well decomposed to worlds which are kind of all correspond to kind of collapsed worlds, in which all macroscopic objects are well localized. So, and there is no really difference between our experience of this theory or this theory. Why I want to believe, why I believe, not want, I really believe that the correct theory is this many worlds theory and not this theory. This looks like more complicated. There are parallel worlds, many worlds. I don't like them. I would like one world. But I don't like even more randomness and action at a distance. This picture requires randomness at action at a distance, something which I don't studied any other course in physics. All physics I study, I don't have it. The only place where I have randomness and action at a distance is in a collapse. So I prefer to say there is no such a collapse. I have to, and I admit that there are parallel worlds. And since for me, this determinism and lack of action at a distance is maybe the most important part of a physical theory, this is why I believe that the many world is by far the best solution of the measurement problem. So I can stop here. So I will stop here, and we'll see if there is some discussion. I also have some section about talking about probability in the many world, which is if this is what if there will be no question, I will maybe go there. But currently, let's stop here.
Thank you, Lev. Thank you very much. So we'll see if we have some questions, but I have two questions that are linked together, perhaps, about probabilities. One of the main issue that is usually raised against everett interpretation is the status of probabilities, because it's very difficult to get a right understanding of probabilities, because everything seems to happen. You have an answer to that, what you call the Born-Vaidman rule. And of course, if this is a postulate that you accept, and it's perfectly possible to accept that, then you have solved the problem, because with your postulate, you give a reason why we have the impression that there are some randomness in the observation. Okay, and of course, with the Born-Vaidman rule, you link the probability that we feel to what you call measure of existence of the world. Okay, and if we accept that, that seems to be okay in this case. But I have two questions about that. The first one is why a lot of people are trying very hard to give justification of probabilities inside everett interpretation that are much more sophisticated and, to my mind, not at all satisfying, such the interpretation with whereas and things like that. We are trying to develop very, very complicated decision theory tools to justify the use of probabilities. And all these attempts are, to my mind, not satisfying at all. If we accept your rule, of course, it's something that we have to accept like that, without any justification, because linking the probability to the measure of existence is totally something that we can accept without any justification. Then we don't need to have this very strange, weird, and complicated explanation from Wallace and so on. And my second question is, could you explain more precisely why the fact to accept the Vaidman, the Born-Vaidman rule is something that helps preventing superliminal transmission? Because I don't see the link between the two things.
I think first there is historical thing. Everett kind of wrote that you can get probability out of a theory. And this was many proponents of many words considered this, okay, many words better than others, because in all other interpretation, Born rule is postulated. And here in Everett, we derive it. People were not convinced by derivation of Everett. And then David Deutsch came with his proposal. And people also were not so convinced, but David Wallace took his proposal and put it in very kind of elaborate way and made a big campaign, and more people believed in it. And also Zurich considered some derivation. So people were trying to derive it, but they were trying to derive it, I think, because Everett said it can be derived. I always said, look, all interpretation, take Born rule as a postulate. It will be very, there are some reason, of course. In collapse interpretation, it's obvious. You introduce collapse, and then you have to introduce what is the probability that this collapse will happen. In Everett, there is no collapse. So where I put this probability? So there is, even before Born rule or any other rule, there is this big problem in Everett. Since everything happened, how you can talk about probability? And usually we all want to know, the physical theory want to know what will happen. I perform experiment, I want to know what is the probability that I will get this outcome. And Everett, many words trying to say that this is not a good question, because I know what will happen, everything will happen, this happened and this will happen. So if you ask me what will happen, everything will happen. And people, I think that is natural to think that there is a diachronic consistency where I will be. Even everything will happen, people were trying to say where I will be. When Albert and Berylor were trying to modify it, they had problems that they had their many mind stories. They say there is a mind of me which will go here, and here I can talk about probabilities, where I will go. So I think first we have to admit the many word picture, when we look on our world, we can look backward in time. Forward in time, there is a tree. Out of this word now will be many words. Out of the, I started my talk, and clearly there are two words. In one, I explained one explanation, in another, I gave another explanation. Then parallel to talk, and then it's very difficult how I can associate myself with two of them. I think Paul Tapanen trying to kind of connect me in different branches if I have different states, but I feel it not appropriate. I can be only in one branch. So I want to discuss only, and well, from the beginning, I want to explain my experience in the past. I have memories of my records. So I go backward, and then there is a single structure. There is a single word of my past. I know I started the lecture. I didn't took this, but there is a parallel branch. It is interaction-free measurement. I'm not there. I'm in teleportation branch. So, and when I look on this branch, I look on all what I know about this branch, I know about results of many quantum experiments, and I have to explain this Born rule. I believe that the only way to introduce something close to probability, it's when I'm in a very special situation, when I'm in particular world, because in action A, somebody moved me, or I moved here, or moved there, and but I know in which world am I. And then I will say, okay, now I will bet about my location. I will not bet about what is. So, in fact, I don't know what is the time scale and what will be as a question. If I would continue with this, I have this other section of the problem of probability. So this maybe is a better way to explain. So
can I just precise my question, because I agree with all you said. The question is simple. We have to justify the fact that we feel that we don't know in advance what is going to happen, and after the measurement, then we see something, and we have to explain that we see something that was not predictable before, and then the solution that you propose is correct to my mind. It's okay. There is no problem with that. You simply adopt a postulate that is taking into account what we observe, and that's okay. My question was not about that. It was about the fact that if we do that, it's okay, and it's an easy solution. But as you said before, Everett was saying that it was possible not to postulate something, but to derive something. And that's the reason why Deutsch, Wallace, and the other guys tried to derive that, but I don't think they succeeded. That's a failure, I think. And my question was, is your rule simply a postulate? Then you just say that you compute the probability from what you call the measure of existence of each world. That's a postulate. We don't have to try to understand that there is no justification. And if you do that, I agree with you in this case. That's a very easy solution. And I prefer that to the very sophisticated and, to my mind, false attempt to derive probabilities inside Everett. So just wanted to check with you that your solution is okay, but it's just the simple fact to adopt a new postulate that is simply to postulate the Born rule with what you call the measure of existence of the world. But of course, you agree on the fact that there is no real meaning to the fact to call that measure of existence. That's something that doesn't mean anything really. And you just have to say, okay, I adopt the Born rule, and that's it. And in this case, I'm okay with that.
Okay, first, one comment about I'm going to perform a measurement and something happened, and now I should talk about probability. I think one can consider classical stories like Book of Parfit, of others. What will happen if somebody make copy of me, 5 copies of me? And this different copy will be in different places. When I wake, what I'm supposed to expect? And in these classical cases, I think usually we will know, okay, there are 5 cases. Probability to be in one of these 5 places is 1 over 5. But it's still, this is because of special situation, because I make several copies of myself. Now about proofs. I think it's important that Born rule, whatever, should be postulated. Because there is ontology. What's ontology? It's a wave function, and there is unitary evolution of the wave function. And this is not connected to the Born rule. Born rule, it's additional thing.
Yeah.
It might happen, everything is unitary, and the Born rule is wrong. There is something different than the Born rule. It doesn't mean that I don't want to say that, that this can be kind of proved. First, I look on my empirical evidence and I know that the Born rule is true. But this is, I also can kind of say that this is natural because of all kind of symmetry. I have my own proof. Everyone has proof of Born rule. I also have a proof. I start with symmetry and with the assumption that we cannot have superluminal signaling. This allows me to prove the Born rule.
Can you explain that? What is the link with the superluminal signaling?
If I don't know if it's let's say we share a particle. I have a particle, half of the particle here, and a half of the particle with you. Superposition. It's not science fiction today. Let's say it has, if it has equal weights, then according to quantum mechanics, according to everyone, according to my measure of existence, probability for me to find this particle is 1/2. And probability for you to find the particle is 1/2. And let's say we have many copies like this. I want to send you a signal. Okay? How I want a signal? If I will change the probability of you to find the particle, this is a signal. If I have many copies, changing probability is sending signal. You agree with me? So if my rule is a measure of existence, you have many copies of these particles. Everyone has measure of existence half. Everyone, according to my rule, has probability half to be found. Let's now take another rule. The rule is that probability to be in a particular word is as 1 divided by the number of words. If I don't do anything, and you measure your particle, you can find it or you cannot find it. There are 2 words. Probability to find it is 1/2. But now, what I do, before your measurement, I take my particle and divide it to many, many parts. Again, the wave packet. And make a measurement in which part it is. Now, for every particle, I create maybe 100 words because there are 100 places where I can find it. And there are 101 words. 100 words that I found and 1 word which I didn't find, and then you'll find it. So when you do measurement now, the probability for you to find the particle is only 1/100. I can decide to make this splitting and measurement or to not to make. I can change the probability in your hand. So if my Born rule is just kind of a rule which usually people who attacked many words says, the probability to be in every word equal. I divide it for every particle to 101 words. So it's equal now. The probability to find the particle in your place is just 1/101. But if I don't do anything, the probability is 100. What's interesting that it doesn't change unitarity. It's all depend on this probability of self-location. The unitarity remains exactly the same. It's not that if I look on all universe together, whatever I do here change nothing in your place. the density matrix of all these particles didn't change.
Mhm.
It's only our concept of our words. Within the word, I will be able to send you signals. So our empirical evidence that in our world we cannot send signals. So I say I know that there is this, I know this, it's also natural. It's also natural because of symmetry. If the words are symmetric, then this is what I know in physics. If everything is symmetric, the outcome should be symmetric. So if there's a symmetric situation, the probability should be symmetric. From symmetry and this non-signaling, I have my own proof of Born rule.
Okay, thank you. Is there any other question?
I see the Alexei one.
Alexei?
Yeah.
Yes, Lev, thank you. I have a very standard question, but I was wondering how you approach that. And the most standard question, of course, is the preferred basis problem. Do you recognize that it exists for in your view? If it does the solution involve this notion of we, or the subject that you are using repetitively, or is there some objective solution? So, because the preferred basis problem, for all others who of course know, but may just a quick reminder, is the question of the basis in which the branching occurs, or the wave function can be divided into different branches in a continuum of different bases. So which one really occurs? Do all of them occur? Which would be a bit strange. So what do you do with that?
I don't think there is a problem of preferred basis. First, I have ontology, and I will explain my experience. And I have a scheme. I have this wave function of the universe, and then I postulate that the wave function of a world is such in which all macroscopic objects are well localized. So this is kind of my postulate of preferred basis, but it's not postulate of any physics. Branching is not a physical process. Branches, it's our concept which helped me to connect my experience with ontology. The ontology is a universal wave function. In this universal wave function, there are many, you can write many different branches. There is maybe one of the questions, can it be some Escher pictures? There are different stories in different ones. And this is not plausible. Also, like I said, I need a Born postulate, but it's natural. And the preferred basis, why this localized thing? Why I would not say, when I have a quantum formalism, and if I look on quantum mechanics, oh, it's something in the Hilbert space, rays, whatever, I don't see any kind of real thing, then I think it's natural to think about all kind of, but I am very settled in 3 dimensions. All macroscopic objects are in 3 dimensions. And I can imagine a life of entangled bodies. I can think about myself. Let's think about myself, teleportation and IFM, tele-IFM, Lev. I can look in, if I look on the universal wave function, I can write this kind, tele-IFM. What will be, so before it was tele, I'm talking to you now, and IFM, I'm talking somewhat different, maybe different times, because I finished in different times. That clearly 2 different. Now I can say there is a tele plus IFM and tele minus IFM. Also 2 orthogonal things. This is what preferred basis is. Why to divide to teleportation basis, where we now discuss it, and the interaction-free measurement explanation, which is parallel world. You say, but mathematically, there is another separation. Tele plus IFM and tele minus IFM. Tele is stable. I remain stable. Now I'm here and I remain here. Teleportation plus IFM, this is what Zurich did, 10 to the minus 40 seconds later, is mixed with tele minus IFM. These bases are not stable. So this is why no creatures, no evolution happened this way. But again, this is kind of in addition. I know that I'm localized, and all my words, all macroscopic objects are localized, so I don't need to discuss it. I'm in this is my frame, the words defined by stories, by my experience. In my experience, everything is localized. And there is a good reason, because interactions are local in 3 dimensions. This is why everything is local in 3 dimensions. I can ask evolution question, why was evolved in this localized creatures and non-localized, and I will answer it's because I have this, there are only local interactions. And sometimes I give another argument. If there is this non-local object, Lev tele and Lev IFM, and I want to drink water. Here I have one glass in this world and another glass in IFM world. If I want tele plus IFM, I need 4 glasses. 2 glasses, it's not enough to me to have 1 glass. I will need, if I will bring to this world 1 glass in superposition, it will not work, because tele plus IFM plus glass IFM will find half of me without water. I need glass in every word. So if somebody will bring me a glass which was not correlated with me, not entangled with me, it will not be enough for this non-local me to drink. He will have to bring 2 glasses. So this is why this other evolution, apart that interactions are local, so it cannot happen otherwise. But it's also, this is why this evolution of non-local objects is not feasible.
It sounds to me, just one last remark. So what you are saying sounds to me incompatible with Everett's own view, which is okay. Of course, you can have a different view, that's fine. But I take it very seriously when Everett, in the beginning of his article, and also in the dissertation, is talking about an observer that can be a machine with memory, that doesn't have to know anything about macroscopic locality or properties like this. So Everett very clearly, for me, departs from the point of view of observer as an agent. He says the observer should have a memory, that's the defining property. When you're using this language saying that I know that there are macroscopic objects that are local in space and so on, I think that this is incompatible with Everett's view on the observer. Which is fine if it is.
No,
but,
I doubt, because I can imagine these non-local creatures. I have works about measurements of non-local variables. And then I have non-local creatures which are entangled. And then they can measure non-local properties of other non-local objects. So I can imagine this. I'm pretty sure that Everett didn't had in mind this kind of non-local creatures. So for all his agents were normal agents. And
yeah, but if you can imagine those guys, then your preferred basis problem is back.
No. What is back? I can imagine universe in which interactions are non-local, and the creatures are non-local. And then it will be strange that I will not need Zoom. I just can non-locally talk to you. or whatever. This is a completely different story, but we are local. I think the locality of interaction is very important for all this many words picture. This is part of the story. This is the wave function, how we can, there is a big universal wave function, and there is this local parts. So this is part of the story. What I remember from Everett, he looked on a kind of wave function in space, and I don't think he looked on this non-local agents. I don't remember this kind of.
No, he didn't. Yeah. Okay, thank you.
Okay. Any other question? Nobody wants to say something else?
I still, if you want, but again, I don't know what is the time scale. I still have this more about probability, but it's more or less what I was trying to say, maybe in pictures. If people are interested, I can go through. But or we can.
I apologize. I have to go in 5 minutes,
Yeah.
but I have 5 minutes more.
So, Hervé, you are the boss to decide what. We can maybe leave it. Maybe sometimes I will come in person, and then I can talk about probability, because this time I didn't talk about probability. Essentially, I decided that during the time scale, if I want to finish without pressure, I'll better not to enter the subject.
I'm sorry, my connection was cut, so I didn't hear what you said.
I said that maybe the better option is to wait. Maybe for sometimes I will come in person, and then I can give a talk about probability in many words, which is
with pleasure.
Yeah,
with pleasure. And of course, we can continue talking outside of this meeting about probability, because I have many questions about that. So, is everybody wanting to ask a last question? Nobody? Okay. So thank you very much, Lev. And well, of course, we continue the discussion by other ways. Okay. Thank you.